Hello, everybody. Welcome back to Channel ANZ Machinery, Modern Metal Recycling and Casting Technology, revolutionizing scrap metal processing. In an era where sustainability and resource optimization are paramount, modern metal recycling and casting technology has emerged as a cornerstone for industrial progress. Advanced facilities today are designed to process scrap metal efficiently, minimizing environmental impact while maximizing productivity and material recovery. One such cutting-edge facility is the full scrap metal recycling plant, equipped with state-of-the-art machinery and processes to handle every stage of the metal recycling and casting workflow. This advanced plant is a testament to modern engineering and environmental stewardship. It includes a suite of sophisticated equipment designed to manage the complex process of turning scrap into high-quality metal products. The core components of this facility include This mobile unit is a crucial first step in the process. The vibratory charging machine ensures efficient and safe loading of scrap metal into the melting furnace. Its mobility adds flexibility, allowing it to service multiple furnaces or workstations with ease. Vibratory technology optimizes material flow, reducing blockages and ensuring consistent feeding, which is critical for maintaining high melting efficiency. At the heart of the recycling operation is the tilt rotary furnace. With a capacity of 15 tons, this furnace employs oxy-fuel firing technology to achieve high combustion efficiency and lower emissions. Its tilting mechanism simplifies the pouring process, while the rotary action ensures even heat distribution, resulting in uniform melting and reduced energy consumption. This innovative furnace is designed to handle a wide range of scrap metal grades, including contaminated or coated materials. T-lip axis side tilting holding furnace with porous plug gas injection. Once the metal is melted, it moves to the holding furnace. This 15-ton capacity unit incorporates lip axis side tilting for precise pouring control and features porous plug gas injection for effective degassing. Removing impurities like hydrogen and oxides ensures the metal's quality, making it suitable for high-performance applications. Mold ingot casting machine with indirect water cooling. After refining, the molten metal is cast into ingots using a highly efficient casting machine with 220 molds. Indirect water cooling ensures rapid and uniform solidification, preserving the integrity of the metal while enabling high throughput. The system's design minimizes downtime, allowing for continuous operation and maximizing productivity. Automation plays a key role in the ingot stacking line. Robots handle the stacking process with precision and speed, reducing manual labor and enhancing workplace safety. A built-in cooling quench further stabilizes the ingots, preventing thermal stress and ensuring they meet stringent quality standards. Air pollution control with continuous emission monitoring. Environmental compliance is a top priority in modern metal recycling plants. This facility is equipped with advanced air pollution control systems to capture and neutralize harmful emissions generated during the melting and casting processes. Continuous emission monitoring ensures adherence to regulatory standards, providing real-time data for proactive environmental management. Advantages of modern metal recycling technology. The integration of these advanced technologies brings numerous benefits. Environmental sustainability. Reduced emissions, efficient energy usage, and effective waste management contribute to a greener operation. Improved efficiency. automation and optimized processes enhance productivity, ensuring the facility meets industrial demands without compromising on quality. High efficiency and low energy consumption translate to significant cost reductions over time. A foundry utilizing kokila or shell molding exemplifies this progress. Kokila, a method where molten metal is poured into a reusable mold, is renowned for its precision and ability to produce high-quality, consistent castings. One notable example of advanced casting is seen in the production of the Saarinen oval table base. This iconic design relies on aluminum cast through kokila, ensuring both durability and elegance. Aluminum, a lightweight yet strong material, is ideal for this application due to its excellent mechanical properties and recyclability. In modern foundries, recycled aluminum is frequently used, aligning with global efforts to minimize environmental impact. The metal is collected, sorted, and melted down before being cast into new forms, significantly reducing energy consumption compared to primary aluminum production. The kokila process offers several advantages over traditional sand casting, including superior surface finish, dimensional accuracy, and faster production rates. These benefits make it a preferred choice for high-precision applications like furniture components, automotive parts, and aerospace equipment. Incorporating recycled metals into kokila casting not only supports sustainable practices, but also demonstrates the potential of combining traditional craftsmanship with modern technology. By leveraging these innovations, manufacturers are meeting the demand for environmentally responsible and high-quality products. The synergy of metal recycling and advanced casting techniques exemplifies the evolution of the foundry industry. This approach not only preserves natural resources, but also sets a benchmark for sustainable manufacturing practices worldwide. The creation of products like the Saarinen oval table base illustrates how these advancements seamlessly blend functionality, aesthetics, and environmental responsibility. Investment casting, often called precision casting or near-net shape casting, is a manufacturing method that produces components requiring minimal or no finishing operations. Its precision stems from the detailed wax patterns and ceramic molds used in the process. The process begins with the creation of wax patterns made from injection molds. These disposable replicas of the final casting are formed by injecting molten wax into a mold cavity. For high-volume production, multi-cavity tools help save costs and increase efficiency. In cases of low-volume production or prototyping, 3D printing techniques like stereolithography can be used to create patterns directly from CAD designs. Wax patterns are assembled into a feeding system, commonly referred to as a tree. This system ensures smooth metal flow during casting and prevents defects. The wax tree is then dipped into a ceramic slurry to form a seamless mold. Layers of ceramic are built up, starting with a fine primary layer for detail and progressing to coarser secondary layers for strength. The ceramic-coated wax tree undergoes a dewaxing process in a steam or flash oven. The wax melts away, leaving a hollow ceramic mold. The mold is then preheated to around 1,170 degrees Fahrenheit to strengthen it and prepare it for casting. Molten metal is prepared and tested for precise alloy composition before being poured into the ceramic mold. The metal fills the cavities and solidifies, forming the intricate external and internal geometries dictated by the mold. Once the metal cools and solidifies, the ceramic shell is removed using vibration blasting or chemical cleaning. The castings are separated from the tree and undergo final grinding and polishing to ensure smooth, accurate surfaces. Additional processes, such as heat treatment, non-destructive testing, and plating, may follow based on customer requirements. Investment casting provides exceptional dimensional accuracy, smooth surfaces, and the ability to create complex geometries. It is a cost-effective and versatile method, making it ideal for industries requiring high precision.